Hello everybody, my name is Federico Camara. I'm here to present DreamSound Deep Activation Layer Sonification. I am a postdoctoral scholar at The Ohio State University working at the ICAD, which is the Advanced Computing Center for the Arts and Design, and also the School of Music. I'm also working here with Matias Delgadino, who is a Hookie Research Fellow at the Oxford University. The two main topics of the paper both involve deep learning in audio signal processing, which has received much attention in the last 4 years. And it is a growing field. In our paper, we outline the main references of this section. Here I will introduce these two topics in what follows. Historically, most deep learning development appeared first on images and then on sound. This is largely because of the availability of large data sets, such as ImageNet, with millions and millions of data. This fact is important because the core element of our research is inspired by an effect that was built for images, which is the Deep Dream project. Deep Dream project is geared towards image generation using layer maximization layer activation maximization on a deep network that was trained for image classification with the ImageNet dataset. The output of Deep Dream can be understood as the pareidolia effect, the psychological phenomenon in which the mind, in response to a stimulus, perceives similar patterns where none exist. Bringing this into sound is a difficult task. So the first work in this respect involved plugging a sound to a Deep Dream generator. Right? To do this, both Balke and Dittmar, as well as Stamenovich, converted sound spectrograms to RGB images and ran the Deep Dream function on the two-dimensional world. This gave interesting results. The problem here is that the spatial correlation of pixels on a two-dimensional image cannot be equivalent to the spatial correlation of pixels on a two-dimensional spectrogram of a sound. We implemented an audio-specific solution using raw audio with variations on an activation maximization function that performs filtering to further adjust the output. An important antecedent that steers away from Deep Dream is Herman's recent work in the visualization and sonification of neural networks. In contrast to the work mentioned earlier, Herman uses a network he trained himself on sound databases to sonify the features that activate a selected layer, yielding impressive results. His research further proves that while lower layers focalize on input localities, higher ones produce upper-level sonic activity, for example, rhythmic and harmonic patterns. In this sense, the results obtained from sonifying layer activations are informative on both input and excitations of a layer. Following the line of these examples, DreamSound can be understood as artistic sonification. The main aspects of the Deep Dream structure are as follows. You take an input image, you compute the gradients of the image with its laws, and you add the gradients to the image at some rate and feed back into the loop. This is basically the activation maximization. While this function gives interesting results in the image domain, in the sound domain, the additive aspect takes precedence. Here we have the input. This is the original sound. Right. And the output is what the first image that you see here, right? This is the whistling. And the gradients are really loud, as you can see. And this is one of the things that we discovered in this research, is that the gradients are some sort of an inversion of the spectrogram of the original sound. This is loud, so be careful. We present the original activation maximization function in relation to 3 filter-based creative variations that were implemented. We find that more interesting results are achieved with this filter-based approach, and there's a lot of room for experimentation. the inputs are taken to build a hard-cut filter that is convolved with the gradients, right? We have the input here, the same input as before. We pass it through the model, and we take the gradients. But we use the filter, the input, to construct this hard-cut filter, and then we add it to the, we turn that into the output. And here, I'm not playing the gradients, but I am playing the difference, and the difference is basically just the subtraction of one of the original of the output of the network of this network and of the input. So this is what it's left of it, basically. So we did a second function that included an addition at the end of this filtering, right? And this addition comes to represent the increment, the small increment that's done on the input. So far. For us, the use of this function yielded more interesting sonic outcomes than the deep dream function. The original sound and its gradients seem to merge better than the deep dream function, and the audio examples using the second function particularly seem to be more expressive. The last function, the target-based activation, this technique is a creative interpretation of a style transfer that was originally designed for images. In our context, this has been called timbre style transfer, sometimes just timbre transfer. The gradients are convolved to the filter, which is constructed by a target sound. Output is a little loud, so I'm going to bring it down. Then we have the hard-cut filter, which is made of the target so that we can listen. Now we have the difference. This is really well, I'm gonna listen to the gradients first. The gradients make more sense. And this is on the 99th iteration, when this target-based activation is run through further. These gradients tend to sort of disappear. And this is a difference which is rather loud, so I'm going to bring it down. The most interesting results occur with a filter-based activation maximization function built from the gradients obtained from an input and its loss. Future work for us consists of adapting DreamSound to take different layers. Right now we're only using the last one because every layer has a different set of dimensions. So we are only using the last classifier, that the last layer that takes out 521 classes. The other thing we want to do is use other models, such as KWGAN, which is another project that we have with Dr. Delgadino. Then we need to assess DreamSound as a data augmentation tool for deep learning, right? We can use this as a data generator for YAMNet or other models. And the very last step is to play and theorize DreamSound as a musical instrument or a sound generator in our artistic work. The code is available as a Python package. You can install it via pip install. You can also browse the source code on the GitHub repository, and the accompanying examples are on the website. Thank you very much.
Thank you very, very much, Federico. And to get this Q&A started, could you elaborate a bit about the use of this tool, artistic and non-artistic, as its applications? How do you envision that?
Hi. Yes. Well, thank you very much. First of all, can you hear me correctly? Well, basically, what we are thinking of is on making a sound generator tool for artistic purposes, right? So I want to use this effect myself. I'm a composer, and I've been using these this tool to generate sounds to build artworks, basically electroacoustic. So that is one of the uses that I'm thinking of. Our our collaboration with Delgadino was mostly based on listening to the output of this uh, uh, um, tool, which enabled us to understand much better what was going on inside of the network of the neural network upon which we trained, upon which we ran this code. So on his side, my collaborator's background is on applied mathematics. So he's investigating one of the loss functions that is inside of this neural system. So when one of the other use that he was taking from this is, well, he was diagnosing basically what's the purpose, or what's the cause of using one type of loss function or another. So that was how we participated, basically, how we collaborated along this time. And the DreamSound research is a first on upcoming collaborations with him and other artists that I have planned. So this is basically our first dealing with this sonification of neural networks project. And of course, this is our first, since this is our first sonification, we're sort of bound to audify what was going on. So since I included this filtering technique, like was mentioning, it sort of steer away from the audifying aspect of it.